Welcome to topic number 22, finding the zeros of polynomial function. Okay, before I show you how to find zero polynomial function, let's take a look at this thing called Descartes rule of signs. All right, so basically what this thing called Descartes rule of sign is a tool to aid searching for zeros. Okay, so you imagine back in the day, a long time ago, before calculator was even invented. All right, how do people actually find the zeros? Okay, because from learning about listing all the possible rational zeros, it can be a lot of choices. Okay, so basically this rule give us a guide on how many positive or negative real zeros a given polynomial has. Okay, it just give a little guide. So we are not really trying to testing out every single possible zeros. All right. So let's take a look at what the rule says. The rule says if you have polynomial function, okay, then the number of positive real zeros, the number of possible positive real zeros is either the same as the number of sign changes of f of x or less than the number of sign changes by a positive even integer. If the function only have one variation of sign, then then the function has exactly one positive real zero. All right, so what does all that mean? All right, let me kind of go over the other one. I will show you. The number of possible negative real zero is either the same number as the sign changes of f of negative x. So what's going on here is normally my function f of x is positive x, substitute in there. So to find the negative ones, I will need to substitute negative x back into my function. So the number of negative real zero is either the same number of the sign changes or less than the number of sign changes by a positive even integer. If you only have one variation of signs, then you only have exactly one negative real zero. So let's check it out. So here's my function f of x, right? So the positive, this x is already positive right here. So right away, I can list the possible positive real zero. All right, all you do is count the sign change from one term to the next term. You see the first term is positive. Positive to negative is one sign change. Negative to positive is another sign change. Positive to negative is another sign change. Negative to negative, no sign change. So I actually have three sign changes. So that means I can have three positive real zeros or less, or it can be less than the number of sign change by a positive even integer. So the only even integer that is before 3 is a 2. Okay, the only even integer is a 2 before 3. So it can be 3 or less than that positive even integer 2. So less than 2, 3 minus 2 is 1. Okay, less than the number of sign changes by a positive even integer. So I can have 3 or I can have 2 lesser than the positive even integer. So 2 less, that means I can also have 1 positive real zero. So it's a guide on how many maybe I could have, how many positive real zero I could have. All right, so the positive ones, I can have 3 or 1. Now, number 2, do the when we do the negative, when we count in the negative positive real zeros, that means I need to substitute negative x into my function. So that's 4 times negative x to the fourth minus negative x to the third plus 5 times negative x squared minus 2 times negative x minus 6. Okay, let's work this out. Negative x to the fourth power is positive x to the fourth times 4 is still 4x to the fourth. Negative x to the third power is negative x to the third times negative 1 is negative x to the third. Negative x whole thing squared is positive x squared. Positive x squared times positive 5 is positive 5x squared. Negative 2 times negative x is positive 2x and minus 6. So let's count our sign change. Positive to negative is one sign change. Negative to positive is one sign change. Positive to positive, there's no sign change. Positive term to negative term is another sign change. So for my negative, real zero, I can either have, once again, a 3 sign change. I can either have 3 negative real zero or less than by a positive even integer. So again, the only even integer before 3 is a 2. So 2 less, that will be 1. Okay. All right, let's try another one, okay? All right, this is already positive x right here, so I can go ahead and count my positive. Let's see how many sign change. Positive. All right. Positive to negative is one sign change. Negative to negative is no sign change. Negative to positive is one sign change. So I can have 2 sign change, or I can have 2 positive real zeros or none, right? I still got to subtract that even number. That even number is 2, right? So 2 less than 2 will be 0. All right, let's substitute negative x into our function so I can count the negative ones. So negative x whole thing to the third minus 2 times negative x squared minus 5 times negative x plus 6. So negative x to the third power is still negative x to the third. Negative x whole thing squared is positive. Positive times negative 2 is negative 2x squared. Negative times negative is positive and plus 6. So negative to negative, no sign change. Negative to positive, one sign change. Positive to positive, no sign change. So I only have one exactly sign change. So for my negative real zero, I can only have one of them. Okay, because there's no even integer before 1. All right, so that's my answer. Okay, so let's give a scenario. For example, if I have 4 sign changes, the even integer before 4 is 2, right? So I can be 2 less. So that means I can have four real zeros or 2 of them, right? Doesn't matter whether it's positive or negative. So if you have 4 sign changes, that means you can have 4 real zeros or 2 less. Okay. Now, what's 2 less than 2 is 0. So I can have 4, I can have 2, or I can have 0. That's the way how we count. Okay. All right. If you have 6 sign changes, if you have a big old polynomial with 6 different sign changes, then if you hold up 6, right? If you hold up 6, you just take, it can be lesser than by the even integers. Okay. So the even integer before, before 6 are 2 and 4. So you can be 2, so you can be 4 less or 2 less. So that means the way how we count it, the easiest way to count this is just go down by 2 at a time, by even integer. So 2 less will be 4, less than 4, 2 less than 4 will be 2, or it can be 0. Okay. That's all the possibilities we can have. Okay. So keep that in mind in a minute when we go over, when you see this on the homework. All right. Let's take a look. How do I find the zeros? Finding the zero polynomial function, we know to find the zeros, we can go by factoring, we can go by graphing. All right. So the ultimate way to find the zeros, okay, of polynomial function is actually a combination of things that we actually use. So when finding the zero polynomial function, if the polynomial function is not easily factorable and the graph does not reveal all the zeros, then we can use combination of theorems, concepts, and techniques to actually find the zeros. So everything that we talk about so far will actually be used. So if you think back, okay, the leading term test, we will need that. All right, we will need to be able to list all the possible rational zeros from topic 20. We will actually use the intermediate value theorems. We will use the even and odd multiplicities. Okay, we will actually use calculators. We will use divisions. Okay, all the things we learned, from the previous few topic will be used here. So let's take a look. Here is a polynomial function, 2x to the third minus 16. How many zeros should a polynomial have at the most? So by the degree, since the degree n is 3, so that means we should have at most 3 zeros. Okay, we should have at most 3 zeros. Number 2, use the rational zero theorem to list all the possible rational zeros. So P over Q, right? Remember, P is the factor of the constant term. Q is the factor of a leading coefficient. All right, so 16. 16 is all the factor of 16 is 1 times 16, 2 times 8, 4 times 4. So when I do my P over Q, it'll be 1, 2, 4, 8, 16 over. All right, Q is 2. The factor of 2 is only 1 times 2. So when I list all my possible rational zeros, all right, I'm going to take all this integer on top over 1. So I should get 1, 2, 4, 8, 16. Okay, let's take all the integer on top over 2. So 1 over 2 is 1 over 2. 2 over 2 is 1, I already got it. 4 over 2 is 2, got it. A over 2 is 4, got it. 16 over 2 is 8, got it. All right, so all these are the positive ones, so I can also have all the negative ones as well. So basically, your possibilities are ranging from negative 16 all the way to positive 16 on the x-axis, basically. That's all your choices. All right, and these are the choice. So why do we learn about Descartes rule of sign is actually trying to give us a guide on how many positive real zero and negative real zeros I can have. Okay, give us a guide on, from this list. I'm not gonna try every one of them. That's crazy. That will be a lot of work to try every single one of them to see which one of them is actually my rational zero. So Descartes rule of sign kind of give us a guide on kind of pick and choose, give us an idea how many positive, how many negative, that we can have. All right, let's take a look at your degree. The leading term test. So 2n to the third power, degree is odd, leading coefficient is positive. So the graph of my polynomial function should look like this one. Okay. So by knowing that, when we graph this function, we will have an idea what we're looking at. All right, 2x squared is 2x to the third minus 16. Let me write my function right here. All right, number 4, how many times does a graph cross over the x-axis? All right, so I'm going to graph it. You need to graph this. Remember, I should have at most 3 zeros. And how many times do I see crossover x-axis? So this is all the graph shows, right? This is all the graph shows. But remember, we just went over number 3, what my graph should look like. So by the leading term test, once the graph going down is keep on going down, it's not curving back. once it's going up, okay, as the x keep on going up, 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 all right, it's actually not what? It's actually not coming back down. Okay, so my graph should look like scribble, scribble, scribble. Right side goes up, left side goes down. And this is all I see. Okay, so this side must be going up, that side keep on must be going down. So how many times do I see it? How many times do I see the graph cross over the x-axis? One time. So what can the possible multiplicity be for that zero cross over the x-axis? Well, if my degree is 3, my multiplicity can be 3 because it can be to the third power, right? If it's odd, that means it will cross. Remember the even odd multiplicity. If it's odd, it will cross. So we saw a cross, so the multiplicity got can be 3, or it can be 1, or it can be 1. Okay, but that may not be this may not hold for true until we actually get to other steps. Okay, so we'll come back to this. Right now, from what I just graphed, the multiplicity can be 3 because this can be I can actually have 3 of the same zeros basically, or I can have 1 of them. All right, how many times do you see the graph turn at the x-axis? We don't see any, so that'll be none. So if it doesn't turn at the x-axis, then the multiplicity got to be none as well. Number 8, use the table or the second count feature to determine a rational zero that will cross over at the x-axis. So that will take us back to the listing. Remember what we listed. These are the numbers that you're looking for. So which one is it? Well, the first thing you do is go to the table because the table will give you all the integers answers. Do you see a 0? Do you see a y equal to 0? Right there, 2, 0. So right now, I already find 1 0 out of 3 of them. Okay. So when I use second calc or the table, determine the rational zero that actually turn or cross. So the 0 I found so far from the calculator is 2. Okay. So you got to think, okay, can it be 3 of the same zeros? Or it's just one of those cross? Okay, that affects your multiplicity. All right, let's think for a minute. I only see it cross over one time, right? Remember the irrational zero we talk about in topic 20. Irrational zeros, the one with the square roots, those are real numbers. So that means those you will see on the x-axis, okay? The one you don't see is the non-real zeros. So if my multiplicity is 1 on this one that crosses, that means the other type of zero I have is non-real zero. So let's assume the other 2 are non-real. We don't know that until we actually finishing the last 2 steps. So far, okay, I don't know what the other zeros are unless I found them. So right now I'm gonna use the rational zero I just found in number 8 and the multiplicity, okay, found in 5 and 7 to perform synthetic division. Okay, that will break down my polynomial. Remember, my function says f of x is equal to 2x to the third minus 16. All right, the 0, I already know 2 is a 0. So using synthetic division, let's break down this polynomial. All right, I do have missing terms. I'm missing 0x squared and 0x to the first. So write down my coefficient, 2, 0, 0, negative 16. All right, bring down the first coefficient. 2 times 2 is 4. Synthetic division, we will add. So that'll give me 4. 2 times 4 is 8. 0 plus 8 is 8. 2 times 8 is positive 16. If I add here, that would be 0. So when we went over the synthetic division before, all right, we say that the last term, the last zero, the last number here is a remainder. So I'm actually not this exponent down. When I perform synthetic division one time, I'm knocking this exponent down one at a time. So this first coefficient 2 is actually 2x squared now, plus 4x plus 8. This is what my polynomial function is right now at the moment. All right. So now, once I get down to quadratic, the whole idea is get your polynomial down to a quadratic. Once you're down to a quadratic, then I can use quadratic formula or factoring, whatever which technique allow me to find the remaining zeros. So just by looking at this, I know this function, I can factor out a 2, right? X squared plus 2x plus 4. But this trinomial actually cannot be factored. There's no way I can actually, having a 4 back here using 2 and 2 or 1 and 4 somehow come up with a 2 in the middle. Okay, so this tells me that I have to use quadratic formula. Okay, I can use the 2, 4, and 8 as a coefficient, or I can use these coefficient. Probably easier to use this one. So my A is 1, my B is 2, my C is 4. So x equals negative b plus minus square root of my b whole thing squared minus 4 times my a times my c. Whole thing divided by 2 times my a. All right, inside the square root, let's see what that is. 2 squared minus 4 times 1 times 4 is negative 12. So this is negative 2 plus minus square root of negative 12. Whole thing over 2 times 1 is 2. So that negative 12 tells me that my answer, the other 2 0 out of the 3 is actually going to be non-real zeros. All right, let's simplify this square root of 12. 12 is actually, these two can go outside as 1. So that's negative 2 plus minus 2 times square root of 3. Got to stay in, right? Square root of negative 1 is an I. Both terms over 2. So my final answer is actually going to be non-real zeros. When all three numbers on the outside can be reduced, I reduce them by 2. So that'll be a 1. There'll be a 1 and a 1. So I don't have to write this 1. I don't have to write the 1 in the bottom. I got to write this 1 at the very beginning because my answer is actually 2 terms. So my answer, negative 1 plus and minus square root of 3i. All right, so degree is 3. I should have at most 3 zeros. So my 3 zeros are negative 1 minus square root of 3i, negative 1 plus square root of 3i, and the 2 that I found earlier. Those are my 3 zeros. Okay, so let's go back up. Our assumption for number 9, the other 2 zeros are non-real. I only knew that when I actually find them. So that means the multiplicity for that one cross on the calculator is actually going to be 1, not 3. Okay, because the other 2 0 is not the same as the 2. So all my 3 zeros are different. So the multiplicity must be 1 over there. Okay, that's everything we learned, or that's a lot of stuff we learned actually put together. All right, let's try a bigger problem. Okay, how many zeros should the polynomial function have at the most? So this example degree is 5. So there will be at most 5 zeros. Okay. Use the rational zero theorem to list all the possible ones. So we done an example like that earlier in topic 20. We said that the P, the factor of P, the last term, 36, was 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6. So when I do my P over Q, 1, 2, 3, 4, 6, 9, 12, 18, and 36 over factor of Q is only 1 and 2. All right, so positive, negative, right? I'm just gonna write positive, negative. I'm gonna go back. Let's go back and take a look at our answers earlier. For topic 21, okay, this is the same function. So I have all the integers, right? Half, 3/2, 9/2. Half, 3/2, 9/2. Half, 3/2, and 9/2. Ah, come on. I'm gonna write all my integers up front. Okay. All right, that's a lot of possibility, right? All right, look at the degree. All right, my degree is odd. My leading coefficient is positive. So my function, by leading term test, my function should look like this one. I'm gonna copy this. Move it down here a little bit. All right, how many times does a graph cross over the x-axis? So I'm gonna graph it. Minus 7x to the 4th plus 22x to the 3rd minus 59x squared plus 36x plus 36. Okay, big old polynomial function. But the graph, the linear test kind of tells me what this thing should look like. All right, one time. Oh, that is not. What is that right there? Is that a term or a cross? Okay, I don't know. That look like is between 1 and 3. So I'm gonna go to my window. All right, I'm gonna go from 0 to 5. Okay, take a look at that 0 right there. Oops. All right, that thing right there was. Oh, that's a turn right there. They never cross over to the other side. Let me make my y value a little bit smaller. Let's do negative 5 to 5, just to be sure. That look like a turn. That's not a cross. Okay. So zoom number 6, go back to standard window. So once that goes up, that will go up forever. This is coming from negative infinity. All right. So how many times did it cross? I only see it one time. Ooh. So there is a. So you got to think about this. Okay. What can the multiplicity be? I see a cross and a turn. Okay. I see a cross and a turn. So my degree total is only 5. So what can that multiplicity be? Well, that multiplicity can be an odd, it can be an odd number, right? So you're gonna be 3, or 1. How so? Well, 3, if the cross is 3, turn is 2. I know turn gotta be 2, so that give me 5, right? So if the cross is 1, that means that term got to be 4 to equal out to 5. Okay. So how many times does the graph turn? 1 time. What can be the possible multiplicity? The possible multiplicity can be 2 or 4. I don't know which one is which yet, so I will come back to this to make sure. Okay. It's tricky. And the multiplicity does matters on the synthetic division too, because if the multiplicity is 1, that means the only 0 you have, okay, you can only use that 0 to perform synthetic division 1 time. If the 0 I found was a term from the graphing calculator, and turn is an even, so that means I can actually use that same 0 to perform the multiplicity 2 times. Okay, so let's go to our table or second calc to see what is that 0. I don't know what that 0 is. Second calc. Oh, that's a 2 again, right? 2 zeros. See, so the one that cross is on the negative. Oh, do you see right here? When x equal to 0, y is positive 36. When x equal to negative 1, the y value is negative 90. So by the intermediate value theorem, when there's a sign change right here, it tells me that there's a 0 between 0 and negative 1. Okay, so far I know 2 is one of my 0, but I need to check. See, by the intermediate value theorem, I need to check, see which one of my rational zeros, which one of my fraction zeros between 0 and negative 1 is actually my answer. So let me go back up. Which one of this fraction one I listed can exist between negative, can exist between 0 to negative 1? Remember, this is both positive and negative, right? 3 over 2 is actually 1.5. This is actually 4.5. So the only one that is between 0 and negative 1 is the half, which is, I can remember I have both positive and negative, right? So I'm going to test out this negative half. Negative 1.5, negative 4.5 is not going to work because I can see it right here. That is between 0 and negative 1. So I go to my second calc and I'm going to go to value and type in negative 1 over 2. And the y value says 0. Bingo, that's another 0. So another 0. All right, I'm going to purposely write this, okay? That one is a cross. The 2 is a turn, okay? Because a turn has an even multiplicity. So that can actually allow me to use that 2 twice on the synthetic division. So remember now, our multiplicity is 3 or 1 for the cross, 4 or 2 for the turn, okay? So I'm still not quite sure, okay? So what happened if this is a 1, this is a 2? That means I'm still missing 2 more zeros. So what type of zeros still remain? Well, if what I wrote here holds true, the other 2 zero that I don't see got to be the non-real 0. But I don't know for certain yet. So I will come back to this. All right. I'm just assuming that my multiplicity right now, okay, the one cross is 1, the one turn is 2, but I don't know for sure until I finding all the zeros. So use a rational zero theorem, okay? Use the rational 0 we found, and then use the, the 2 rational 0 we found and the multiplicity. Let's perform our synthetic division real quick. All right, so there's no missing terms. So that's 2 negative 7, 22, negative 59, 36, 36. I'm going to use that term first, okay? The term is 2, easy to use 2 first. Okay, bring it down. 2 times 2 is 4. Since that division, we will add. That's negative 3. That's a negative 2 times negative 3, negative 6. 22 plus negative 6. So that should be, oops, 16. 2 times 16 is 32. All right. So that division we will add. So that should be 27. Negative 27, excuse me. Negative 27 times 2, negative 54. 36 plus a negative 54, negative 18. And 2 times negative 18 is negative 36. My remainder is 0. So right now, this 2 exponent not down by 1. So this 2 is actually x to the 4th power. This is actually 2x to the 4th power. Okay. So I'm not quadratic. I'm not quadratic yet. I only knock it down by 1. So if I assume I know the term have at least multiplicity of 2. So that means I can use that same 0 again to perform my synthetic division. So I'm going to go again using 2. So hopefully you begin to see exponent was 5. I'm going to use 2 twice to break down that exponent. That will take it down to x to the 3rd power. Then at last, I'm going to use that half. I know the cross multiplicity is 1, so I can only use that half 1 time on the synthetic. Then that will allow me to drop down to x squared. So from x squared, then I can see what the other 2 zeros are. Then I would know what my multiplicity is. All right, bring it down. 2 times 2 is 4. So that division we will add. So that's going to be 1. 2 times 1 is 2. That's 18. That's 36. Negative 27 plus 36. That should be 9. 2 times 9 is positive 18. So that division we add, that's a 0 right there. All right, I'm going to use half now. Okay, bring down the 2. Half times 2 is 1. 1 plus 1 is 2. Half times 2 again is 1. Did I do something wrong? It's half, right? Half times 2 is 2. Half times 2 is 1. 1 plus 1 is 2. Half times 2. Oh, yeah. All right. So this is going to be 19. No, that can't be right. Where did I go wrong here? Oh, I'm sorry. Crap, not half, negative half. Sorry about that. Now the other 0 was a negative half. I saw on the calculator negative half. Sorry about that. I was about to say, why didn't it work out? All right, negative half. All right, negative half times 2 is negative 1. If I add 0, negative half times 0 is 0. Add them is 18. That's going to be negative 9. Add them up is 0. Okay, so now this 2, see this was x to the 4th, x to the 3rd. Now this is x squared. So my polynomial function has finally been broken down to 2x squared plus 18. All right, so I can use quadratic formula to find this one, or I can use, since I only got 2 terms here, I'm going to use square root property. All right, set the function equal to 0, 2x squared plus 18. All right, 2x squared is positive, move the 18 over. So that will be negative 18 equal to 2x squared. If I divide both sides by 2, that's x squared equal to negative 9. If I take a square root on both sides, my x is actually equal to positive negative 3i. There you go. So the other two zero were non-real zero. So because the other two zero were non-real zero, so that means my multiplicity on the cross got to be 1 because I only used it one time earlier. I only used a half, negative half one time. So that term multiplicity got to be 2 because now the one time it crossed, 2 for the turn, so that's 3 plus the other two non-real 0, 4, 5. There you go. So it is not, understand this now, this is not, I have at most 5 zeros, right? I have at most 5 zeros. So now it turns out 2, negative half, 3i, and negative 3i are my zeros. So I should have at most 5 zeros. Well, the reason why you only see 4 because the 2 has a multiplicity of even. So that's even multiplicity. That's 1, that's 1, that's 1. That's odd. So that's how we add up to be degree 5. All right. Let's try another one. This one's not as bad. All right. How many zeros should I have? 4 of them. All right. Let's write it out. Our P over Q. Q here is 1. Okay. So the factor of 1 is just 1. So 15 is 1 times 15 and 3 times 5. So this is not as bad. It's 1, 3, 5, 15 over 1. So my possible rational zeros are simply 1, 3, 5, and 15. Okay, there's no other number here. So I know when I look up in the calculator, I don't have any fraction ones, right? I don't have any fraction one, got to check. All right, leading coefficient is positive, degree is 4. So this should be what my graph will look like. Let me copy this. I can graph it here in a minute. I'm gonna put it down here also, okay? Let's graph it. X to the 4th minus 2x squared minus 16x minus 15. 1, 2. Ah, you only crossed 2 times. Okay, I don't see 4 times. All right, so number 4, how many times does it cross? Got to be 2 times. What can the possible multiplicity be for those 2 crosses? All right, remember degree is 4, right? So you gotta think about this. Okay, degree is 4. I have almost 4 zeros. Each cross, okay, each cross gotta be an odd number. So I can actually have one of them with multiplicity 3, the other one with multiplicity 1. Okay, so I can have 301 again. Okay, because that add up to be 4. All right, do I see any term? No, did not see any term. So there's no multiplicity for the term. All right, let's check in the calculator. By leading term test, once it goes up, See these number keep on, these y value keep on going up. As x going to the right, once the graph go up, it keep on going up. Okay. All right. So I know my integers are positive. I mean, all my possible zeros are integers. So that's 3. What's the other one? 3 and -1. Awesome. Okay. So if I assume both of these cross has multiplicity of 1 on 1, because my degree is only 4, right? So I need to break it down using 3 and break it down using -1. That's all I needed. I only need these zero. I only need to use them one time to knock this 4 power down. So the other two I don't see. The other 2 zero I'm missing right now. I think they are non-real zero. But remember, irrational zeros, you can see those on the graph. Okay, you can actually see them cross, but you actually cannot find them unless you go through the unless you use the quadratic formula. All right, so let's use the rational theorem. Use the 2 rational zeros I found, and then let's perform our synthetic division. So what do I have? 3 and -1. I'm gonna use 3 first. I do have a missing term, which is 0x to the third. So that's 1, 0, -2, -16, -15. All right, bring it down. 3 times 1 is 3. If I add, that would be 3. That will be 9. So that's 7. That's 21. And that's positive 5. 3 times 5 is positive 15. Remainder 0. All right, so this is 1x to the third now. So I'm going to use the other 0, -1. So bring down the 1. -1 times 1 is -1. Synthetic division, we will add. 3 plus -1 is positive 2. That's -2. Add them up is 5. 1 times -5 is -5. Remainder is 0. So this, now my polynomial function has been broken down to 1x squared plus 2x plus 5. All right, this cannot be factored, so I got to use quadratic formula since I got 3 terms here. So -b plus minus square root of my b squared minus 4 times my a times my c, whole thing over, 2 times my a. All right, let's see what's inside this square root. So 2 squared minus 4 times 1 times 5. That'll be -16. Ooh, -16. Square root of -16. So I know square root of -16 will become 4i. So all 3 number on the outside. Oh, hold on a minute now. Darn it. That's not -2, that's 1. So all 3 number on the outside can be reduced. We reduce them by 2. So that's -1, that's 2, that's 1. So I don't have to write the 1 down here. So that would be -1 plus minus 2i. All right, so my the other 2 zeros are non-real 0. So my zeros are 3, -1, -1, minus 2i, -1 plus 2i. Because the other 2 zeros are non-real 0, so the only possible multiplicity, so number 9 is right, the only possible multiplicity for the 2 crosses got to be 1 each. Because if a multiplicity is 1 and 1, then that give me 2 plus the other 2 non-real 0. Add up together, give me 4 zeros. All right, let's go over the homework. Oh, it's right here. All right, same thing as what we just did. Which type of zero would not be shown as crossover term at the x-axis on the graphing calculator? The only one that will never show is the non-real zeros. The irrational will show up. All right. For the following polynomial function, apply Descartes rule of sign. So these are the positive ones, right? So I just want you to determine the possible number of positive real zero. Just do the positive ones, okay? See how many sign changes it? And then do the or part, right? Make sure it's two less, okay? Less than an even integer on what you counted. All right, number 3. So here is your polynomial function. So hopefully you kept the answer from the listing of number 2, listing all the possible rational zeros. Okay, so you can type it in here. So this one, tell me how many zeros this polynomial function can have. All right, number 3, circle your answer. Okay, choose which one should be that actually by the leading term test. If you when you make a choice, just circle it for me. All right, by looking at the function, okay, number 4, graph the polynomial function, see how many times it crosses, okay, and make your prediction on the multiplicity. See how many times it turns, make the prediction on the multiplicity. Just exactly the way I did, I just show you, but you got to make sure you come back here, okay? You got to make sure you come back and, to 4 and 6 once you found your other zeros. So okay, so you can actually have the correct answer here. I wrote 3 or 1 earlier just to as a prediction. Okay, maybe it can be 3, maybe it can be 1. I don't know which one is which until I find out what the other two zeros are, because the other two zero could be the same one as the one I found in the calculator. Okay, in that case, then my multiplicity can be 3 or it can be 4, whatever the even or odd number is that I predicted. All right, so make sure once you find the other two zero, come back to 4 and 6, okay? All right, number 8, use a graphing calculator to actually find your actual rational zeros, okay? So you already listed out, you already listed here for number 2. So just go through your list and see which one, especially the one that cross or turns. All right, and determine what should be the other two, and whatever which one you choose, just circle it for me. Perform the syntactic division for me right here. And then once you perform the syntactic division to break down your polynomial function, then use a quadratic formula to find the remaining zeros. All right, so just real quick showing you how to find the zeros of a polynomial function using all these things that we learned in the past few topics. All right, thank you for watching.